Okay,
Okay.
so hopefully all of you can hear us.
Yes, I can. Can you hear me?
Okay,
Okay. Okay.
so as a quick introduction about myself and embedded meetup. So first of all, my name is Ahmed Magdi. I will be your host along with Professor Max Santos. We are greatly honored to have Mr. Santos as a speaker today. Professor Max is an associate professor in electrical engineering department in Universidade Tecnológica Federal do Paraná. He worked in large organizations like IPM, Volvo, and General Motors, and he also has led over 14 R&D projects being managed with over $1.3 million as a budget. So for those who are first time to join us, Embedded Meetup is a non-profit professional community with focus on sharing knowledge and providing opportunities to fellow professionals to sharpen their skills and get exposed to the latest technologies. We have been working for more than 1.5 years. Our main activity is monthly webinar that addresses one of the technologies and solution related to automotive and the communication and other embedded system related industry. So we had also other activities like few offline workshops, like evaluation program for those who are seeking to get uh, new opportunities, job opportunities, and improve their skills. So we are also planning to host an open source projects in the or open source projects in the near future to maximize the cooperation between community members. So our largest percentage of our audience are from Egypt, but we have also other audience from other countries around the world. So I think maybe it's time to start.
I think we lost the voice from Ahmed Magdi. Professor Max, can you hear me?
Yes. Okay, I
Okay.
can.
Sorry for the audio quality issue. Could you please maybe start? I think Magdi will join us soon.
Okay. All right. Uh, can I get started? Hello.
Yes, please. Yes.
Okay. Thank you.
Thank you. Thank.
Let me first share my screen. Uh, I'm doing that. Share the screen. Okay. Let me check if you are seeing my screen. Can you see my screen?
Yes, we can.
Yes. Okay. Let's check if the my slide is being able to you see also everybody. Can you see my slides?
It is visible. Thank you.
Okay. All right. Thank you, Ahmed, for your invitation to me presentate present here. Thank you, everybody, special to the uh, embed the community from Egypt. It's my pleasure to be here. And my name is Max, and today's presentation is about on the toward a centralized vehicle architecture. Okay, as you gave you the presentation, introduce myself. Thank you very much for your kind introduction. My name is Mauro Dias Santos, and I'm associate professor at UTFPR. And I manage many projects here in Brazil, especially my research group GSA, Grossa 2030 and FINEP 2032. The main questions are assumption. What is the software-defined class? First question is, the second question is, why is this so important? So the question is, what do you need to know about software-defined class? These are three main questions that you can do, and I will try to respond them throughout this presentation. It's just a simple disposition about the differential of what? Wait, what? Hello? Sorry, is there any problem that you cannot hear me? Okay. Can on? Can on? Or no? Okay, that's good. Well, where am I? Here you can see the world map. Um, we have the South America region on the left of the world map. Brazil is part of the South America, is a country. Here we have in south of Brazil the Paraná state. Specifically, I'm in the region of Ponta Grossa city, and here we are at the UTFPR University. My research group, named by GSA, or in Portuguese means Grupo de Sistemas Automotivos, we are passionate to make research science and technology. Then we design, build, and test new smart algorithms and advanced control strategies in accordance to methods, process tools, and standards to deploy, build, and deploy in current and next generation of the road and the fly vehicles in order to become more clean and safe, smart, and enjoyable, of course. These are the group of governors of the GSA lab. I'm the coordinator. We have a technical lead and we have a secretary. We are proud of with our numbers because we are a lab that has many projects from Novaral to Automotive 2030 and FINEP 2030. We have more than $2 million in funding from the industry and the government. We have more than 40 grants, scholarships for students paid by industry and government too. 3 vehicles that you can do tests. And our students are, in general, employed in industry, university, and the government. This is the overview of our lab and the list of partners that you have. What do we have and can we do? Well, we can design, build, and test new algorithms and control strategies in terms of the ADAS systems and the autonomous driving too. We also have some activities in terms of the to develop new control strategies and algorithms to engine control to IC vehicles. The four main stages of distributed computing we can see here split by years. In 1960, we had a concept of the mainframe. In 1980s, we had the concept of the end application of the personal computing. In 1990s, we had the ability provide some database that we had applications that demands a high volume of the resources of data, And for this, we had application but demand for a huge volume of data. In the years of 2020s, we had a different topology because the distributed computing was widely adopted. But currently, we are going to the back in the 1970s to the centralized computing systems. We are show here just the IT evolution along the years. The same evolution we can apply to the automotive systems. What is the case in transportation systems? CASE is the acronym of the Connected Autonomous Share and Electric Vehicles. Is the ability to apply this technology in order to provide a better conditions of transport peoples and loads more easy, friendly, efficient, clean, safe, and comfortable to everyone. Currently, we have maturity, technological maturity to apply this vehicle, but think it to leverage the vehicles to become more autonomous as possible, as soon as possible. Well, we can see here on this slide a bunch of the vehicles because you don't have just the vehicle in terms of the passenger vehicle, but you have also sport vehicle, we have electric vehicles, we have also, for example, buses, machine vehicles, construction vehicles, agriculture, and many other types of road vehicles. What is a road vehicle? First, automotive system. For definition, a road vehicles is a set of subsystems that integrate them, like powertrain, body, chassis, infotainment, and many other subsystems that we can integrate them in order to build a passenger car or a commercial vehicle uh, that has the ability to take people and the loads from the point A to point B. In terms of the control and management of the vehicle, we can see the evolution in four main stages, from manual to autonomous. We can see in the X the time, of course, and the Y-X, the autonomy level of road vehicles. First, we had the manual propulsion systems because the vehicle was able to transport people in the loads, but use it as a propulsion system as an animal. Second, we had the evolution to the automatic systems. This is an example of the automatic transmission systems. Uh, this functionality allowed to the drive vehicle without do the task to change gears. And this task could be done by software automatically. Third is the adaptive systems, a set of sensors put surround the vehicle that is able to perceive the environment and help the driver to drive more safety and comfortable. And the last stage that we are working on is the autonomous vehicle, comprised in a bunch of sensors like LiDAR, radar, sonar, ultrasonic sensors, cameras, in order to the vehicle drive alone without the driving intervention, for example. In terms of the complexity and the time for development of the vehicle, we can see that complex cars is more simple when we compare to train, ship, plane, and NPP, that means nuclear power plant. And in terms of the time for development, cars are put in the different level because it is more fast to develop a car than you develop a train, plane, or NPP. However, it lost to time for development when compared with ship. In terms of the innovation of product and manufacturing, we can highlight about the many innovations, many new products and manufacturing that Elon Musk is doing. We can see this picture, a picture from the Model Y is a Cybertruck vehicle, a full electrical vehicle developed and manufactured by Tesla Motor Company. Tesla manufacturing. Of course, that this car was designed, and everyone knows about this new product with high quality, electrifying the no emissions and the many other important features. This is the innovation in terms of the product. We also know about the innovation when Elon Musk launched the Model 3. It's a passenger car, the second car developed and built and the sold by the Tesla Motor Company. But Elon Musk doesn't innovate in just in the product in terms of products. We can see a, a huge innovation that he promotes in terms of the SpaceX, and we can see here a new model of the manufactured car. We don't see here, we cannot see here any robots or manipulators. And where are they? This is a new way to build these kinds of car, vehicle, Model Y. The new models of vehicles or cars or new concepts of car for a long time were presented presented in specific shows, specific events for the automotive cars. However, today we have a competition between where the automakers can show the novelties in automotive systems. We have here an example in 2018, the Detroit Auto Show, and this event happened in the United States, like in Germany or France and other kinds of events, that the OEMs like GM, Ford, and the Renault and others uh, could present the novelties in terms of the vehicle. Very innovations could be presented in this type of event. But today, currently, as a vehicle has a huge amount of software contents, they prefer to present the innovation in this type of event. Consumer Electronics Show, this is an event uh, promoted in Las Vegas in the United States every year. The technological innovation in mobility, we can see or split in three, four, depends on the granularity of aspect that we would like to highlight. But we can see here the technological innovation in mobility in three main stages. In terms of the period of time, today we have a vehicle that you need to have a driver to transport people and loads. But this vehicle has an engine or internal combustion engine to propulsion systems. We have also some products that has a propulsion system, a hybrid vehicle, and we have also some vehicles that has a propulsion system electric motor. The human drive is the main component that can um, move this vehicle throughout the roads and the many other uh, environments. Second, tomorrow we have the same vehicle but with a different infrastructure. We have here just a framework that you can put the body in different configurations. But we can highlight four main steps or four main items. This vehicle has a propulsion system made by engine, hybrid or electric, but you have a certain level of autonomy, level 3 and 4 in terms of the autonomous vehicle. And finally, in the future, we have many types of vehicle that can transport peoples and the loads uh, from the point A to point B, whatever the place. But there are a large amount of drive trains that we don't have also the drive in this case. We we are working to reach this level 5. Here we have the evolution of the automotive systems, or the mobility is more suitable to say instead automotive. We have the traditional vehicle with the IC engine, IC propulsion system. Second stage, we have the electrified vehicle that is a vehicle that has at least one electric motor. Of course, that we need to have a storage system. A storage system is the capacity is a component able to store energy in like battery, supercapacitor, fuel cell systems. And in the third stage, we have the driver system systems. And the fourth stage, we have connected vehicle. That is the ability to the vehicle connect with infrastructures, many other infrastructures, components, pedestrians, cyclists, and many agents on the road in order to provide the environment more safe and comfortable, efficient too. In the fifth stage, we have the autonomous vehicle, and in the last, we have mobility as a service. Well, what is how can we define the automotive product development cycle? We can define the main stages to us design, build, and test vehicle. But in terms of the product, we can split in four main stages. The first one is the market. Market is the ability that we use techniques to see what kind of product the market is requiring. Secondly, after we receive the demand of the market, we have the engineer team comprised by different profiles that together can build or design the vehicle and test if they attend the specification in the first stage of the development. After we wish to develop a high volume of vehicle, and this is the manufacturing. We have to set up many machine tools to develop, to produce, manufacture, produce many vehicles in a certain period of time, for example. And finally, we have the after sales that are the specific houses able to do campaign or to fix a vehicle or to repair and many other tasks, activities after the consumer buy the vehicle. The main actors or stakeholders for this for this stage are OEM, original equipment manufacturer, like General Motors, Renault, and Ford, and many others. And we have also the support from the supplies and the tooling. And we have also another stakeholder, aftermarket. We can see or can show us show to everyone about the three main stages in terms of the structure of the company. We have the engineer team that has the ability to design and build and test the products. We have the manufacturing team that has the ability to set up different machines in a facility in order to produce vehicles in large scale with different models. Finally, we have the after sales that you have of workshops, 24-hour services depends on the manufacturer and the OEM and the other assistance centers. All these three main stages are the automotive engineer. So, in terms of the product, we have the automotive subsystems. As I mentioned before, automotive systems is a set of subsystems that integrate them, is able to take uh, peoples and the loads from the point A to point B, but in grounds. Uh, we have a mechatronic systems that is able to us control with a better performance and efficiency. And for this, we have to put sensors and actuators. Sensors is the transistors are the transistors able to measure physical variables, and actuators are the transducers uh, able to actuate in many physical variables too. However, we have also embedded the system, a specific computer to control these mechatronic systems. And the embedded systems comprise in three main software components that they are the software to control and management to do control and management of different subsystems like powertrain, chassis, body, and many others automotive subsystems. Currently, we have vehicles with more than 100 ECUs. For each subsystem, there is a specific ECUs. This is a big problem because when we increase the number of functionalities of features, we of course will increase the size of network. And the another software component is diagnosis during the production line, or for example, during the development of the product, we have to measure variables or we have to calibrate vehicles. We have also, after sell the vehicle to the specific customer, we can need to fix the vehicle, update or do a campaign. And diagnostic is the ability to do everything. And they also we have the component enabled by supervisor. Supervisor is a software component that like a watchdog that can monitor all the hard and software if they are really operating correctly because this is a critical system. We can see here the workflow of a specific company, for example, Daimler Chrysler, for example, that show us the all stage of the development uh, for the engine control system. We have three levels. In the upper level, we have mechatronic vehicles system, where we have, for example, to build uh, the engine block, mechanical block. In the second level, we have the electronic control unit, a hardware that is designed to control these mechatronic systems, for example, these mechanical systems. But this is a mechanical system that has hydraulic and the pneumatic components that you have to manage in order to not, for example, uh, leave the engine with high temperature because can take the engine to the failure. And in low level, we have the embedded real-time software that we develop the control strategy and the advanced algorithms, for example. Well, moving to this slide, you can see also a graphic with the x, and here we have the yx. What does it mean? Well, in XX, we can see or describe the evolution of the complexity control management intelligence of the vehicle. We can have vehicle less smart or more smart. We can have a vehicle less complex or more complex, and so on. side means the less complexity, on the right side means more complex. And the y-axis show us also the levels less or more, but in terms of the flexibility, efficiency, performance, and autonomy. We can split in terms of or divide in four main stages in terms of the engine control. The first stage we have is mechanical control, a carburetor. That is a mechanical component that was developed a long time ago and it could control vehicle, but we were able to improve the fuel consumption and emissions, and we have had a limitation. Were a hard time to optimize the engine management. Second level is the analog controller, but we could stay very stuck to the specific model. For example, we could have designed an analog control for a specific model A, but if you wish to change for another model B, for example, we are not able to do that. This could be solved by the electronic control unit because we can change the application of the ECUs by exchange just the software component, for example. The same ECU hardware could be applied to model A and B, but with different calibrations, of course, but made by just by software. The hardware were the same. And currently, we are facing for the software-defined cars or software-defined vehicles, simple, saying in a simple way, software control. We have just one hardware that all the applications or different applications are managed by this app, like a mobile system. However, we have another component, maybe by artificial intelligence, and this kind of technology needs to have an advanced method process and tools to design, build, and test because the traditional methods are not suitable or doesn't fit more for this kind of technology. The next generation of ADAS system, this is just a simple example. We can define in two main parts in terms of safety systems. Safety is different from security, but we can give some examples in terms of ADAS systems. ADAS passive safety systems like lane departure warning, forward collision warning, and many others, blind spot monitoring systems. However, we have the second level of the safety systems, the active safety systems. The example of active safety systems are adaptive cruise control. Today we have cooperative adaptive cruise control, and the newest level is the platoon systems. AB, autonomous emergency brake, and the lane keeping system. But why am I say this for you or present this for you, and what is the relationship with this topic, the topic of this presentation? Yes, because the answer is currently the vehicle is able to perceive the environment in a limited form. As you can see here, a car that is able, with different sensors, is able to see the environment just in 180 degrees of perception system with radar and the camera, for example. And the ADAS today has many ADAS systems, but for AB, we have just one ECU. LKA, QA, we have another ECU. ESC, we have another ECU. For each ADAS feature or function, we have a specific ECU, And when you put more ECUs in the car, we have a bunch or a large network of ECUs. This is very difficult, complex to design, build, and test, of course. And the trend is, oh, why not we develop just one ECU, and as we have now to a trend is to smart sensors. We can have just one ECU, one computer systems that connect different smart sensors, and these computer systems is able to support many ADAS systems. And this is the ADAS feature, ADAS for tomorrow. AB, LKQA, and ESSC are all in one. Is a collection of ADAS features that can be put in just one ECU. We don't have more, no longer, the one ECU specifically for one ADAS feature, for example. We can see here that the vehicle is able to have 3D surround vision in 360 degrees, for example, a better performance. What do we have and can we do in this situation? Well, we can see here three levels of ECUs or distributed architecture for vehicle. In first stage, we have a distributed ECU that we are facing currently. The vehicles that you have nowadays have this structure architecture, and the second stage is domain centralization, and the third stage is the soft-defined vehicles. The same idea of the current smartphones. Domain and the zone architecture means that we have different levels, domain architecture, and we have also the zone architecture. And we have to think that we vehicle has many power systems uh, and also signal distributions. And we have to have also a power distribution model for zone ECU architecture. What is uh, what is this so important? Because currently we have many sensors that are smart sensors that has the ability to measure physical variables and actuating physical variables, but pre-process information to deliver to the processor more fancy, more fast, or more exactly without noise, and to relieve the ECU to spend more energy or power in terms of the processing. Self-development efforts into the domains. You can see here that many efforts are done in terms of the middleware. We have a vehicle that, for example, the auto technology, over there technology. The same situation, a great example of the auto is the Tesla vehicles that they are able to the user change the performance of the vehicle without we take them to the workshop, for example. Here we have the distribution where we can have many innovations in terms of the vehicle, in terms of the body and the energy, powertrain, chassis, infotainment, connectivity, security, and connected services. The ADAS systems in autonomous drive is where the field we have a large avenue to do innovation and do new things. So the next slide, I will provide you some definitions that can give us a background to understand better about the software defined vehicles and also the zone ECU or distributed ECU. Here we have this slide to define or show us about the vignettes. Vignette means vehicular ad hoc network. And we have here in the city, of course, that you can uh, describe in three different environments that the road vehicle can move in rural, in cities, and in highways, for example. And all vehicles are a piece of code, a computer systems, a computer on wheels, and IoT components that have the ability to communicate with other vehicles, pedestrians, cyclists, infrastructures. But of course, that in the city we have to have the RCSU. RCSU is a roadside unit. Is a component that can communicate with many base stations of 4G or 5G, and now we are going to moving to the 6G that has the ability to, for example, communication and support many different applications, not simple applications like transmit single variable like temperature, positions, and the velocity and the main other single variables, physical variables. But 5 and 6G uh, are technology that can allow us to uh, transmit information like video and information from LiDAR and many others, video, of course, images. Here we have to understand a little bit about this technology, cloud, fog, and edge computing. In terms of the data storage, we have three levels, from low to the low level to the up level. We have the edge computing. This is the computer system device that has the ability to store data that the application will require to processing, and the very fast. And of course, that in the level of the edge devices, we can run real-time applications. But for computing is the ability to we have a distributed storage system to store application also in the data, but in another level when you don't have the capacity to store in my uh, devices. And finally, we have the cloud computing that is widely used. But cloud computing, we have data centers. But for example, a long time ago, for example, we had a vehicle that should be fixed, and you should to take them to the workshop. But currently, with the new technology of the communications and the IT, we are able to fix many cars in real time using the cloud computing without the necessity of the user have to go to the workshop. And we can change the application, the firmware, and many other technologies, many other components in order to improve the performance and efficiency of the vehicle. So when you talk in terms of the self-defining cars, I'd like first to show you a little bit about the other names close to self-defining cars. These three examples show us or give us a good definition to a good background to understand why self-defining cars is important. So, self-defining network is one great example. On the left side of this slide, you can see a traditional set of suites. A suite is a network equipment, network component that can receive packages from IP, for example, Internet Protocol, receive from one side and process and uh, send it to the right destination, for example, and find there are many algorithms and that can route the correct messages. And there are many protocols or many technologies that can provide quite of services. Suppose that you have many applications and like applications that demand for real-time communication, applications that demand, for example, bandwidth and many other requirements. Quality of services can be implemented in specific suite. However, we have a good or a bad description definition of this traditional architecture. All these switches are spread and they are operate without standalone. And one switch A doesn't know about the state of the switch B, and no one operates in the integrated form. On the right side, you can see the soft-defined network. It is a new modality, a new concept of the suite because all the controller uh, major method that you had into inside into switch now is made by a specific control machine, and this control machine has a specific software that know the states of each switch, and these switches are programmable, and this allow to the system be more efficient and controlled, and do the network much more affordable and much more efficient, much more fast, and attend all requirements or quality of service demanded for the applications. The self-definition of soft-defining everything is the soft-defined storage. But here we can see on the right side the traditional soft-defined storage that you had many copies. We had a large database, and you had an interface that can provide these data sets on this database that can be stored and processed in recovery and distributed to all application. We had a large data center that had, for example, to to guarantee the fault tolerance. For example, we had the dual controllers, single platforms, storage management softwares, but all of them are centralized, of course, or distributed too, but in a different way. And today we have a soft-defined storage that you have SDS management as a solution, and a platform more safe, of course, more available, can provide this scalability and many other features. So we see here two definitions of soft-defined everything and soft-defined networks, soft-defined storage, and now we have the third example. And after we show, this is just a motivation why soft-defined car is the top level or the height content of the vehicle nowadays. It is the trend of the automotive system. This is the software-defined infrastructure is a set of components that have different resources and can be managed by one, controlled and managed. Control and management are important words because we wish to control the components and we have to manage the systems. And we can see that the resources A, B, C are distributed, but we have just one center of control and management that can manage these resources in order to everyone know information for each one, for example, a specific another specific resources. This is very important because you can uh, take this architecture to the more efficient with better performance to apply or to use or run applications. And then now, finally, we have here the definition of the soft-defined cars. Soft-defined vehicle or cars, the same we usually say cars because a vehicle can be road vehicle or fly vehicle or ship vehicle. Is a term that describes a vehicle whose features and functions are primarily labeled by software. Software is a central point of this new concept, this new technology. So before QHunter until now, we had the system based on hardware, and the next generation is motivating for the autonomous vehicle, electrify, shared, and they also uh, connected. We have the software-based systems. A software-defined car has many components that allows us to have different features to attend the next generation of the automotive systems. It allows to us have features and functions, update firmware, scalability is the wish of the OEM, automotive original equipment manufacturer like GM, Ford, and the Renault. Zone oriented, not more subsystem oriented, for example, because we have a large ECU. Uh, Currently, we have an ECU that controls specific subsystem, but the zone ECU means that you have a set of, we define an area that comprises different subsystems, and we have just a ECU that control all these subsystems in the best way, in a better way. Connected vehicle, of course, automation, flexibility, and also centralized. What is the difference between function and feature? This is a good definition to us understanding apart these functionality or these words. Function is the goal of that is able to accomplish with a product, service, product, process, system, practice, application, machine environments. For example, a road vehicle that can move, taking people and loads from the point A to point B. In feature, we can give an example like wheels. Wheels is one component, or steel wheels also. Is a one component that can be integrated to the road that enables to the function operation, the main function of the vehicle. In the future, new features can be activated by drivers, and the examples are services, features, functions, and or applications. Softwares allow to contract and price models, where new features can be integrated as are customized services to the driver. The vehicle will be able to communicate with the environment, collect data and real-time operations, and send to the cloud, of course, because we don't have capacity to storage a huge volume of data. Vehicle need to have wireless communication, connected vehicles, and the technological trends in mobility are, of course, the uh, that are causing the transformation of the mobility are electric, connect, share, automation, driving, and mobility services are primarily made possible by software. But what is the difference of these two words, HDC and SDC? HDC means hard-defined cars, and the SDC means software-defined cars. HDC is the traditional architecture, hard-defined cars, and the SDC is the next generation architecture for the vehicles defined by software-defined cars. This is a simple example of the architecture of the modules. In the vehicle, we have also different network levels and the different size of ECUs. The time of ECUs means the capacity of processing and the capacity of data storage, for example. Here we have also a new architecture. We have three different central processing units with a huge capacity of processing the power to feed the sensors and actuators. And this um, this electronic control unit we use the basic paradigm of the embedded software. And software-defined cars, we have the zone computing unit, ZCU, and we apply the technology of the software-defined cars. And the main hardware that we can apply for the next generation of the automotive systems, of course, that we list here, I list here in terms of processing, of course, that we have the different applications, but MCU, microcontroller unit, ASIC, application specific integrated circuit, FPGA, DSP, digital signal processor, GPU, graphic processing unit. Graphic processing unit is a type of CPU, uh, a large CPU that is able to process a huge volume of data in parallel way, but use it to the high performance computing, use it to process information like application like visual computing and the artificial intelligence algorithms. HSA is a heterogeneous system architecture, is a type of computing that we have different uh, a group of computer systems like FPGA, DSP, GPU together with a huge volume of processor. See, depends on the application. Quantum computing is the trends. Uh, the trends of the software-defined cars is the same as to the mobile system smartphone. We have a hardware, and depends on the computer resources we have in this hardware, you are able to put infinite or many applications like WhatsApp and like Facebook and many other applications. Architecture transformation uh, in three levels: today, tomorrow, and future. As I mentioned before, software for the development efforts into domain. The main view of this is device management system. These vehicles require update, for example, or require new features, for example, and we have a device management systems, and we will need to have the cloud computing. That is a new technology, as I showed you before in the beginning of in middle of this presentation, I presented the definition of the edge computing, fog computing, and cloud computing. And cloud computing is required when you wish to update firmware, apply a new application to the vehicles. Um, I guess that is someone or many of you here know about the AUTOSAR. AUTOSAR is a software, is a pattern to this automotive software architecture that define very well or clear the structure of the software architecture in the vehicle. We can define the software component developed by the industry and the basic software with the basic functionality with any call and the hardware, of course, many other components. But this architecture where was divide, defined and established many years ago in order to think to the future that we had the ADAS systems until to today. The system had many features and functions that you could split, and this architecture, classic AUTOSAR, was very helpful currently. Before AUTOSAR, you had, for example, RTOS specific for automotive systems. We had those EC, for example. But the next generation of the automotive system, of course, that the classic AUTOSAR is not more, is no longer great or good to be adopted because the concept of requirements are totally different. And the came up the new concept of AUTOSAR, adaptive AUTOSAR, that's the enable of the, for example, features like technology like over-the-air update. And we can see that the new technology software-defined cars depends on the over-the-air auto technology, and also depends on the adaptive AUTOSAR. And we can see here clearly how this technology can be integrated, but in the future, of course, that the trends will have just adaptive AUTOSAR. This is the overview in two parts. On the left side, you have the structure software architecture of the classic AUTOSAR, and on the right side, you have the the, the adaptive AUTOSAR platform, AUTOSAR adaptive platform. We have different components, of course, because here in the classic AUTOSAR we have a definition of the application, sensor, and actuation, and we had an easy definition of the AUTOSAR interface. But here on the right side, we don't have an easy definition because we have another intermediate or like a middle interface named by ARA. ARA means AUTOSAR Runtime for Adaptive Applications. Because one single example of this, the motivation of the AUTOSAR Adaptive is in AUTOSAR Classic, we have we could apply for the vehicles that we have many simple sensors and actuators, and also we had simple software components, more static with a specific application, and we don't did demand for more complex software. In the for the automotive, the AUTOSAR adaptive platform is to the next generation because you have the AI, you have another sensors like, for example, cameras, lidars, and many others. And the complexity, of course, to our storage information, process and the recovery are much more complex. We have here a draw of a picture of the existing system, currently the classic AUTOSAR, and the future of the AUTOSAR, the adaptive AUTOSAR system. Depends on the naming. But existing system is based on the RTOS named by OZEC VDX. Here we have the AUTOSAR RTOS, and here we have the new RTOS for the adaptive AUTOSAR. Okay, this is a simple example too, that we have an evolution from today to the future. Today we have single smart sensors and actuators. The next stage we of course demands for more safety vehicle, and the third stage we are demanding for performance and efficiency. In the future, close future, in 2030, for example, we will demand for high performance computing. Of course, that you have also to think in terms of the fly vehicles too. The other motivation, OTA motivation is this is a single example why auto is so important. The conventional method to update a vehicle was current method. We had a manufacturer of vehicle, of course. We had a software that we could update in vehicle when the owner, the user of the vehicle, take the vehicle until the workshop to the vehicle mechanical update software. This mechanical use the specific tool to update this software in vehicle. Currently, the user will not need to take the vehicle until the workshop because the manufacturer of factory is able to send the update through the network, through the cloud computing, using the auto technology. There is an auto center for this. This is another example, but just as an illustration. It's conventional update method and the auto based update method. Of course, that each company has their own, for example, solution. But there are suppliers that provide solution to the OEMs, for example. And the OEM define the requirement specification, and the supplier will provide the solution, the technical solution for this. There are patterns, standards that can manage this technology in the future. This is very important to have standards. Other firmware benefits, bugs and product behavior can be continuously improved even after the device is in the hands of your customer. Of course, that you can, after you buy a car or vehicle, you can update or find bugs and the remotely online. OEM can design, build, and test new features by sending updates to one or multiple devices at the same time. Of course, it's more easy, simple, and also cheap. OEM can save costs by managing the firmware across the fleets of devices from a seamless, unified interface, and suppliers and developers can deploy frequently and reliably, know that products will stay functional and updates are released. These are the main benefits of other firmware benefits. Other firmware is the basic infrastructure that we I show you in the AUTOSAR adaptive, for example, simple example. Auto firmware augments scalability and flexibility. That is the two main features, two main properties that automotive industry desire by adding in new features and infrastructures to products as they are released. Of course, that when we are talking in terms of the computer on the wheels, we have to have attention in terms of the attack by hackers, and we have to deploy technology for the security, not safety just, but the security. Because during transmission, we have to apply technologies or methods to avoid some malicious attack can came up, for example, during the transmission. These are part of our work, a work that I do with my colleagues from Pakistan, for example. We propose a framework with the SDN OTA, and this framework is very not we developed, but we did publish yet because this work is under evaluation, and we simulated this structure. Mainly, we have the application, we have also in the middle southbound APIs, and in the low level, we have software-defined vehicles architecture that we define in order to update or upgrade all vehicles components when demanded by the user, for example. Trends are going to be like this, change the automotive industry paradigm from component owner to feature owner. I work at the General Motors. I was a release design engineer at the and the engineer design. Uh, but today we have the feature owner, not the component owner. Software is the key element of the next generation of automotive system. Demand for high software complex leverage to the evolution of the hardware. And the evolution of the hardware is required by the evolution of the software, of course. So uh, the the use of GPU is demanded more for the complexity of the artificial intelligence algorithms and video processor algorithms and the high performance computing algorithms, for example. These three main applications demands for powerful uh, computer systems like GPU, for example, or the trend is high heterogeneous system architecture. Innovation methods, process tools are no longer helpful or great for the next generation of the automotive system, and we have to develop new methods, processes, and also tools. And they hope to the standard uh, be ready to apply. Consider the AI application with demands for the different methods for design, build, and test software, telecommunications infrastructure such as 5G, and there are many places in the world that work on the 6G are the key aspects to enable device communicate. Visualization might support to find bug virtualizations, might support to find bugs and speed up the time to market with more quality and customize. OEM and suppliers adjust update their operation for this new age of the mobility. Okay, this is the reference of this application. Then, and so uh, that's it. Thanks, Falk.
Professor Max, we would like to thank you very much for your volunteering for today's webinar and for this enlightening and entertaining presentation. We appreciate you taking the time to be with us today. I think we have a couple of questions if we have time to handle them.
Okay.
Okay, so the first question, it's regarding the implications of usage of the service-oriented architecture. So, in terms of security and safety of passengers, or how this could complicate the security and the countermeasures of.
Okay, great question. I did mention more details about the safety and the security here. I just gave you one overview, but of course that you have to change updates. For example, the ISO 26262 standard for uh, this new technology, and in terms of the security also, we have also to change some things or update. In terms of the security, I think that there are being considered in terms, for example, to the new architecture of the adaptive AUTOSAR and the new architecture of the OTA and the um, in terms of safety security, as I mentioned before, we have to uh, define a structure that attend these new requirements. Because safety is very important to the next generation of vehicles, and of course, security is the same, we can say. But there are many aspects that I can share with you after this presentation. If you contact me, feel free to contact me.
Okay, thank you. And the next one is a request. It's related to the presentation. Is it possible? Oh, I think we lost Professor Max. We do apologize for the connection issue. I think we can wait for Professor Max to rejoin, and if it's not possible within 5 minutes, we can forward the questions to him.
I ask you apologize because my connection down. Sorry.
Welcome back, Professor
Oh,
Max.
sorry.
No problem. So we have a request from related to the presentation. Would it be possible to share the
Of
presentation?
of course, I can do
Mhm.
that.
Okay, thank you.
No problem.
Um, and also, the next question is related to standardization, or as you mentioned earlier, we for safety we should comply to the ISO 26262. The question here is related to the V2I, or vehicle to road infrastructure. Is there any common way or common standard between OEMs to implement this?
Yes, of course. Of course, that you currently at the university we do simulation in terms of simulation, but of course, but I don't have access to the OEM. But
Mhm.
each one defining their own architecture, of course. But I don't have access to say more detail about this. I'm so sorry.
Okay, thank you.
There are many software. Yes, of course.
And finally, a question about expectations. When do you think that the OTA would be supported for all the vehicles? Do
Yes,
you
of
have, yes, please?
great question. Great question. Of course, but of course that you have a transition because you currently don't have all vehicle available in the world or in specific region with this technology. But the trends, of course, is to be support to all vehicle. We have to think in terms of the different applications. For example, in passenger cars, we can see this technology well largely applied to the Tesla vehicles, but all the automakers are working to provide the same solution. In terms of the commercial cars, of course, that we have, if you have a fleet of vehicles, this is a great technology. Auto technology we provide to us exchange or send the software, update software, but can change also many operation models, like in terms of the agreement between the dealer and the user and the to know information about the user experience and the many other uh, features that can be explored. We are facing for a huge transformation in terms of data is has a huge volume of value, has a huge volume of data available to us, and you have to transform this data, apply data science, of course, to the new feature, extract new new business, of course, to the mobility. Depends on the region and the application that you intended to apply, for example, to to give more benefits to using the of course to the automaker, to change the operation model of the automakers, and there is a large avenue of the opportunities.
Mhm. Okay, thank you for this answer. And finally, we have a thank you note, and would like to thank you again for your time and for volunteering for this webinar.
Okay, thank you everybody for having me. Thank you, thank everybody, and thank you, Ahmed, for your invitation and the attention, and that's it. I wish you hope that everyone can have a great weekend.
Thank you very much, and hopefully we will get a chance to meet again. And
Okay, for me, a pleasure.
adios.